네, 이제 마지막 사실 제일 중요한 어떻게 보면 로버트 하버마이어 그 대표이에요. 폴카닷 대표이자 공동 창업자고 나이가 엄청 어리지만 정말 천재급이죠. 그래서 작년에 말에 한국에 와서 저를 처음 만났는데 그래서 같이 제가 미더도 듣고 했는데 너무 친구가 똑똑하고 예, 그래서 진짜 감동을 받았었는데 이번에 또 와서 발표를 하게 되네요. 그래서 궁금하신 거 있으시면 뭐든지 물어보시고 최대한 천천히 하라고 말할게요. 그러면 좀 더 듣기 쉽게 예, 하실 것 같아요. Ready? Yes, you're ready. Speak a little slow. 박수 드립니다.
Yeah, thank you everyone. Thank you to Erica and to Spark Plus for helping us host. I see a few familiar faces in the audience. I see some new people. It's really great. Thank you everyone for coming. The talk I want to give right now is about Polkadot for developers. Like, what does it actually mean to build on Polkadot? What does that entail? You already got really in-depth descriptions of what parachains are, for example, from Adrian, how the consensus works from Alistair, what our overall vision is from Ryan. And I want to talk a bit about, okay, how do we actually build this thing? I would want to start, and this was sort of the theme of my talk at Biddle, is like, why do we care about interoperability at all? So if you're wondering about scalability, like blockchains aren't scaling that well, a naive solution is just add more blockchains, right? We could run 5 Ethereums or 10 Ethereums or 10 Bitcoins, and then we can do more transactions per second that way. But we lose network effects. All of a sudden, if you have 5 Bitcoins, you have an account on one, but that money isn't accessible from any of the others. So we need the network effects because that makes the applications we can build more powerful. You want to be able to actually transfer value with companies or people that you want to. So what Polkadot is really about is like adding more chains to increase scalability, but also maintaining the network effects. And this is really the value proposition of parachains. You can create new blockchains so that you can process more transactions worldwide. These blockchains can be very specialized, so they're very good for specific purposes, that they can be for machine learning or for the Internet of Things, or for just flat out really good payments, really fast payments, for smart contracts. There's so many applications that you could use parachains for. And if any of you are running a company that has thought about building a blockchain, now is probably the point where you're wondering, how do I actually do that? So without further ado, I'll talk a bit about the design principles. So one, we want it to be heterogeneous. We have many different kinds of parachains that do specific things. We want it to be scalable, again, on-chain and off-chain. That means supporting innovations in layer 1 and in layer 2. And we want it to be secure. And Alistair is really the one who does a lot of the heavy lifting on this, is defining rigorous and formal models of security for the system, especially in the consensus and data availability layers. So we have two sides of a blockchain. This is how I like to think about blockchains. We have the state machine. So the state machine is what does the blockchain actually do? Does it do payments? Does it do smart contracts? What is a transaction? I mean, people will say, this blockchain does 1 million transactions per second, but they don't really talk about what is a transaction. And this differs vastly from use case to use case. So that's defined by the state machine. The state machine tells you what your transactions are. And the consensus system is how do we agree on which transactions were included? What is the global consensus on the state of the system? So the consensus is a lot of work to put together. So our design principle in this sense is give developers the freedom to be free from thinking about consensus. That when you're a developer or a team with a new idea on blockchain, typically you have an idea for a new state machine. So some new idea of how to process transactions that's going to change the way these things work. So Polkadot is really all about giving developers the freedom to work on those state machines. And then we have interoperability. You have your state machine, which does this specific thing, and it can send messages between other blockchains that have their own state machines that do their own specific thing. So for example, you could have a decentralized exchange chain. And you could have a smart contracts chain. You could have one for the Internet of Things. And these can all talk to each other, which means that you can build applications that live sort of on all three chains at once. It also supports, one example that I'll go into a bit more is we have the public and private chains running in the same network. That you can define state machines which are sort of defined as being valid because they are signed off on by a consortium. So you can have public chains and you can have these private or consortium chains, and those can also interoperate with the other chains in Polkadot. And another thing that this means is that we all have the same consensus mechanism that provides security for all the parachains. So all the parachains have pooled their security. You have the communities of all of these parachains, rather than competing amongst each other for limited mining power or limited staking resources, that they're pooling their security, and you get a more secure system in the end. So now I'm just going to really dive into how exactly you would build a parachain. So the technology that we use, you're not really bound to use Rust. You can use anything which compiles to WebAssembly, but for the development of Polkadot and for the development of Substrate, we are actually really big fans of Rust. So Rust is sort of like C or C++. It's as fast as either of those, but it has, it allows you to prove the safety of your program, that it won't crash, that there are no buffer overflows. Basically, all these little holes that exist in a lot of C and C++ programs that hackers and attackers can exploit are actually impossible in Rust. So for that reason, we're really big fans of it for this kind of environment. WebAssembly is used to actually execute the parachains. When you are a developer and you write your state transition system, you're writing a piece of WebAssembly code that's run by the Polkadot network. So you don't write the WebAssembly directly, you write some code that is then transformed into WebAssembly, but in the end it is WebAssembly. And we use libp2p. Again, you aren't bound to that, but we find it to be a very nice set of tools for writing complex, well-organized peer-to-peer networks. So a parachain, and you did get one aspect of this from Adrian, but I'd like to go into the other aspects a bit more in this talk. You have a validity function. So basically, this is a piece of code that you can run, and it tells you if a block is good or if it's bad. So that's what the Polkadot network uses to check the blocks that come from parachains. You have a collator node. So this is like a blockchain node. It's something like a miner or a proof of stake sealing node is today, in that it's watching for new transactions in the network, and it creates new blocks with those transactions. So it's pretty simple. It creates the candidate block with those new transactions in a way that block, when it gets passed to the validity function, says that block is okay, and then the collator sends that block to the relay chain, to the validators, so that those validators can actually see that the block is good and then vote on its security. And lastly, the last thing you have to think about is the message queues. We have messages passing between parachains. When you write your parachain state transition, you have to think about the messages that are coming into your parachain and going out of your parachain. So what Polkadot looks like when you actually write that code is you have just this one function you have to write, more or less, which is execute a state transition. What was the last header? What's a proof of that block's validity? So that might be like a Merkle proof of all the accounts that were touched during the execution of this block, and the new messages in. And this returns maybe the new header and the messages coming out of the block if that block was good, or if the block was bad, it returns nothing. So WebAssembly gives you the power to write this function, fill it out as you like, with C or C++, which many of you are familiar with because they're hallmarks of this kinds of system computing for the last 20 years, but also Rust, newcomers like Rust or perhaps even Go, languages that can fill that niche. And writing the collator node is not that easy, it would seem, because you have to actually write a piece of software that participates in a peer-to-peer network. It has to look for transactions and figure out which transactions to include. So Substrate, which was mentioned a bit by Ryan, gives you this basically for free. You can write parachains using parity Substrate that will essentially just create this Polkadot node for you without any additional effort from your part. So just to go into an example of like what that validity function would look like for the bank chain, you have a bank chain. It's curated by a consortium of banks. The state transition of the chain is checking that the block has digital signatures from the entire consortium or the majority of them. So no aspects of how the state is actually changing are public. It's like the consortium can say, well, Joe has $1 million now because we say so. And that's how that chain is defined. So that means that you could have, for example, banks issue tokens that other networks can use, and these tokens would be backed by actual collateral by that consortium. So this is, more generally, as a bit of a non sequitur, this is sort of where I see the direction of banking going, maybe in like a post-blockchain world, is that rather than having something like fractional reserve banking being the primary goal of banks, where they're doing a lot of different trading on very limited collateral that they hold, that rather they are designed to just provide collateral for blockchain-based financial applications. That they're essentially banks of trust, and that's really it. And for the bank chain, you can produce outgoing messages and handle incoming messages arbitrarily. So to talk a bit more about Substrate, this is something that could have a whole 45 minutes talk on its own, but basically this is just a set of libraries for doing all the things that are really annoying about writing blockchains. So writing a database, writing a chain synchronization algorithm, the logic of actually creating blocks. Again, when you're writing a blockchain, most of the time you don't really care that much about this stuff as long as it's happening efficiently. What you care about is the unique state transition that you and your team have come up with. Substrate is really designed just to make that possible for you. So just a really quick overview of what the Substrate stack looks like. You have libp2p, which manages a peer-to-peer network. The peer-to-peer network is participating in a consensus process that executes WebAssembly code to decide on which state transitions of a runtime have happened. And the runtime is made of many different modules. So those modules are like pre-written components, almost like from an app store that you can plug together with other ones that you've downloaded or from the ecosystem, or ones that you've written yourself. So some of the ones that we've written so far are ones for certain types of governance, for a DAO treasury. For Polkadot, we wrote a module for parachains, but you could actually take that code and put it in another code base if you wanted to. You have modules for producing randomness out of the blockchain, and those sorts of things. You could write your own modules as well, just to make it your own unique spin. So I'll skip this because we don't have that much time, but if you're interested in this, we have the ability to upgrade chains in Substrate. If you have a chain and you made updates, you can upgrade the logic of that chain without having to hard fork. So if you want to find out about that, just talk to me afterwards. So here's an example of what a cross-chain smart contract call looks like in Polkadot. Basically, we have messages that are passing between chains. So imagine that chain A and chain B are talking to each other through the Polkadot relay chain. So chain A has a piece of break-in logic that's called every single time a new message comes in. And it knows how to interpret those messages according to some specific format. So chain B sends a message to chain A. Chain A says, oh, I can see that that message is a smart contract call to one of my internal contracts. And it interprets that message, dispatches the call, and you've just done a cross-chain smart contract call. Just to speak really quickly about governance, upgradability is a huge portion of this, especially for non-controversial changes. We embrace the idea of on-chain governance. We have a sort of bicameral system. We have two houses in the on-chain governance of Polkadot. So there's a there's a council, and then there's a coin voting system. But one kind of interesting thing to think about is that parachains can participate in the governance of the network. So parachains, when they get attached to Polkadot, sort of put down a bond. They lease their parachain slot from the network. And parachains can actually vote with those tokens. But how the parachain decides how to vote with those tokens is up to the state transition of the parachain. So you could have parachains that are dispatching voting power based on any arbitrary mechanism, which means that the governance is open to support any kinds of voting mechanisms that parachains can encode. So just to take inventory really quickly of our roadmap and where we are and where we're going in the next couple of months, what we've done so far is proof of concept 1. That was towards the beginning of this year. It was minimal governance, as I described, proof of stake, a basic user interface, and the forkless upgrades. We used that to upgrade to proof of concept 2, which was the first parachains implementation. So back in towards the end of July, early August, we had the first initial parachains deployed to test Polkadot networks. Now we're gearing up to release proof of concept 3. So that's the implementation of the hybrid consensus that Alistair just described. It's called Grandpa, and we're using Aura from Parity's proof of authority consensus mechanism for the block production. Where we're going now is interchain messaging. So proof of concept 4 is going to give the first implementation of interchain messaging. It's at this point that I like to describe Polkadot as being ready for developers. So this is where, from the perspective of somebody writing a parachain, you're basically feature complete. And all the future proofs of concept, 5, 6, and 7, so on, are really just going to be about implementing slashing conditions and providing more security to the network. So in parallel to all of this, we're building developer tools for parachains, particularly Substrate and a Rust-based domain-specific language specifically for writing blockchains, because typical programming methodologies don't always map that well onto the logical computing model of a blockchain. So we're writing a special programming language based on Rust specifically for that. So I'll wrap it up there. Thank you very much for coming. Yeah, I think we should just open the floor if you have questions. I think you have all been sitting long enough. If you have questions, please come up to me, just ask. Thank you very much.